Welcome back to Dave Does Math from Home. We're following up a very exciting section, 8.2, with part 2 of section 8.2. In the last video we did a lot of theoretical explanations for why integration by parts works and where it comes from. And in this video we're just going to do a bunch of examples of integration by parts so we can see what that looks like and how we're going to use it. And as a reminder, the integration by parts formula is the integral of u dv equals u times v minus the integral of v du. So I'm going to start with an extremely simple one, probably about as easy as they get. We have, I want the integral of x times e to the x dx. So we can see that this is an integration by parts problem because we have the product of two functions and multiplication isn't safe. Neither of these functions has an inside or an outside. It's just two things multiplied together, no composition. So we're going to have to use integration by parts. Once we've made that decision, the next decision we need to make is one of these parts needs to be u and one of these parts needs to be dv. That's important. We're not choosing what u and v are. We're choosing what u and dv are from among our available functions. And then based on what u and dv are, we're going to use that to find v and du. So generally speaking, if there's a polynomial piece, like just an x or an x squared or an x cubed, just like x to some power, that piece should probably be your u, because when you take the derivative of that to get your du, that's the one that's going to become easier and easier and easier to deal with. So if you start with an x as your u, then when you find du, it's basically just 1. So that's going to work out really nice for us. If you try to let your e to the x be your u, it's not going to get any simpler when you take a derivative. The derivative of e to the x is exactly as complicated as e to the x is, so nothing to be gained there. So we're going to let that be dv, e to the x dx, so that v is e to the x. So one of these pieces you take a derivative of and you want that to get simpler when you take the derivative. The other piece you want to be, you're going to take the integral of, you're going to do an antiderivative. And you want that to hopefully not get more complex. So dv should usually be your e to the x's, your sine x's, your cosine x's. Those things don't really change in complexity. You can take lots of antiderivatives and they just sort of stay the same basic kind of thing, which is great. They don't get worse on us. X's, or natural logs, those things get easier when you take the derivative, so those make excellent choices for you. These are sort of heuristic guidelines. There's no real algorithm for it. Sometimes you want to do it the other way. Do it a lot of times and you'll get a sense for what should be what. Once you've got all of your pieces identified, we can just sort of plug this into the formula. So this integral, which is u times dv, is going to be u times v, x e to the x, minus the integral of v du. And hopefully at this point we can pretty clearly see that this is really easy. And that's sort of the goal of this. We're going to replace the integral you have with a different integral, and if you choose your u and v correctly, this integral will be much, much, much easier than the one you started with. So, yeah. We have x e to the x, that part's not changing, minus e to the x plus c. This is our integral. So let's do another example. look at the integral of x to the fourth natural log x dx. After I just finished explaining that we should usually choose our x terms to be u, let's try that. U equals x to the fourth, then the derivative there would be 4x cubed, and that's fine. That means that dv would be natural log x dx, and now we're a little stuck. To get v, we need to integrate the natural log, and that, believe it or not, is something we haven't done yet. When I do this in classrooms and full of a live audience, as it were, lots of people try to tell me that v should be 1 over x. It's a very tempting answer to give, but that's the derivative of natural log. What we need here is the antiderivative of natural log, which is not 1 over x. It's natural log does have an antiderivative. We just don't know it yet. It's not something we've done in class before. So we'll get there, but not today. And because we end up in this, I don't know what's going on here situation, that just means we probably made a poor choice for u and dv, which is fine. We can erase this very easily. Nothing of extreme value was lost, except maybe 10 seconds of our time. And you weren't going to do anything important with those 10 seconds anyway, let's be honest. So, let's just try it the other way, see if we get better results. I'm going to set u equal to the natural log x, which means that the derivative there would be 1 over x dx. So far so good. 1 over x seems easier to deal with. dv is x to the fourth dx. And I can take an antiderivative of that. It would just be x to the fifth over 5. No problems there. So, this integral should equal u times v. So, x to the fifth, or let me start using coefficient fractions. Those will be a little easier. 1/5 x to the fifth ln x is what happens when I multiply u and v together, minus the integral of v, x to the fifth over 5 times du 1 over x dx. This thing, as written, doesn't look much simpler than this thing we started with, but this thing simplifies really, really nicely. So let's take a moment to simplify that. This part will stay the same, 1/5 x to the fifth ln x, nothing's changing that. I'm going to take the 1/5 outside of that business, because coefficients are safe. The x to the fifth over, I'm not actually going to write that, x to the fifth divided by x, that's just going to give me x to the fourth. And now I think we can agree that this is a much easier integral than what we started with. Integrating x to the fourth is a better plan than trying to integrate x to the fourth ln x. So, final answer is 1/5 x to the fifth ln x minus 1/5 times x to the fifth over 5 plus c. You could turn this into 1/20 x to the fifth over 25 if you wanted to. I won't, because I'm profoundly lazy. This is a good example of when you're doing integration by parts and you don't want the power function, the polynomial piece of it, to be your u. You want the natural log to be your u, so that when you combine its derivative, 1 over x, with the integral of this piece, you still just have a power function, and it's nice and it works out. So there's that one. What else should we do? I think that it's time we talked about what happens when you have to do integration by parts a couple times. So let's look at the integral of x squared cosine x dx. As usual, let's let u be x squared, du would be 2x dx, and let's let dv be the cosine of x dx, and then v would be the sine of x, and that's fine. This is very similar to that first example we did in the first video. It's just x squared now instead of an x. So we can run this through the formula. U times v is x squared sine x minus the integral of v sine x times du 2x dx. So this thing here isn't much easier than what we started with. We started with an x squared cosine x, and now we have 2x sine x. So we still have this product thing happening. We still have the product of two different functions in here. All we've really managed to accomplish is we've reduced the degree of this by 1. But that's good. That's progress. We can do this again, and we'll reduce the degree of it by another 1. And eventually we'll get down to a degree 0 piece, and then when we have the degree 0 piece, that's just a constant, and we'll just be left with a trig function, and we can integrate the trig function. That's the plan. Sometimes you have to do integration by parts 2 or 3 times in a row to get the answer you're looking for. So I'm going to start doing integration by parts again here. First I'm going to take the 2 on the outside. It can go out there. I want my u to be the x, and then du is just dx, and I want my dv to be sine x dx, and then v is just negative cosine x. One of the very common mistakes students make when they're doing these is they go the wrong direction with the pluses and negatives on their sines and cosines. We're doing integration by taking derivatives of some things and antiderivatives of others, and sometimes sine turns into a cosine and sometimes sine turns into a negative cosine depending on which direction you're going. So be very, very, very mindful of which direction you're going for each of these pieces. Here we want an antiderivative of sine because it is the derivative of something. So to get the original thing, we take the antiderivative, and that's negative cosine. So I'm going to turn this into a big arrow so we can just start working on this whole thing. This piece doesn't change. That's done. X squared sine of x, that's done. We are subtracting 2 somethings. The something we are subtracting is the integral of this, and this is the integral that we are replacing with this business. So now we're going to do u times v, so that's going to be x times negative cosine x. This is u times v. So now I need to subtract the integral of v negative cosine x times du. That's just the dx. This is what we wanted to get to. If you have a power function here, x squared, you do this twice and it turns into 1. If you have x cubed here, you do this 3 times and it turns into 1. If you have an x to the 6th here, you do it 6 times and it turns into a 1. You can always reduce this in degree every time by doing this process. And the other piece, like as we take derivatives of the x squared to get 2x and then 1, or if this was an x to the 6th, every time we take the derivative of that, 6x to the 5th, 30x to the fourth on 120x cubed. We can keep going there down that path as long as we want. Each time we're taking an integral of this trig function, and it's kind of not changing. Like it's cycling between the different trig functions, but it's never going to get worse. It's always just going to be one of the trig functions, and we can always handle one of the trig functions. So that's what it means to do integration by parts over and over again. You can always turn a power function eventually with enough derivatives into one. I'm not going to make you do one with like 6 or 8 pieces or whatever. Like, if you can do it with 2 pieces, that demonstrates to me that you know how iterations work, and then you can, that's fine. So I'm going to finish this one and then be done with this video. There is a part 3 that we need to do, and that will start in a moment. Let me finish this one first. X squared sine x minus, no, I'm going to do plus 2x cosine x, because it's minus minus. And then this is going to be, again, plus 2 is the minus minus. Or, oh, maybe I can pull this outside. So maybe it really should be minus 2. The integral of cosine is just sine, right? That's it. These get long, they get kind of tedious, but they don't ever really get difficult. I think, at least. Like, some of them may take longer than others. They'll be time consuming, but all of the individual steps of what you're doing are all pretty straightforward. You have a formula, you follow the steps, you use the formula. If it takes you 10 minutes, it's 10 minutes well spent, and it's not some sort of insurmountable challenge, I think. Anyway, there is more we need to talk about. For example, I need to show you how to do the integral of a natural log. It's possible with this technique. We'll do it in part 3, so stay tuned.